this norm induces a metric. So what would be
F minus G.
the meaning of Fg? So it's going to be norm of F minus G, which is same as the square root of inner product F minus G and F minus G. Okay. So inner product not only induces a norm but it also induces a metric actually. Okay. Which we call it induced metric. So here's the definition of what we call Hilbert space. So roughly Hilbert space is a complete inner product space. Okay. So which is Hilbert space. If it is complete. Okay? Now here's a serious question. What is the meaning of completeness in inner product space? So when I am saying that, yes, using Nietzsche. So when I am saying that this space is complete, okay, I mean that it complete with respect to this induced metric activity.
Yes, sir.
So if you take any Cauchy sequence, in H, okay, and it turns out to be convergent with respect to this metric norm, your space is Hilbert space. Okay. So it's a complete inner product space is Hilbert space. So I'm writing, I'll do one example and one non-example. I must write that. So when I'm writing this, I mean this is an inner product space. Here's an example. I would like to write it in the terms of theorem. L2 is Hilbert space. L2 is Hilbert space. Before that, shall we not talk about KD? But KD will be roughly the same kind of argument that we have there. Anyway, I'll quickly comment over KD afterwards, because that is also. How can I prove it? So I know that L2 is in a product space. The only thing that I need to show is that take a Cauchy sequence in L2 and try to prove that that Cauchy sequence is convergent. So let Xn be a Cauchy sequence. What we would like to show that it's convergent. And when I'm saying that Xn is a Cauchy sequence in L2, okay, let me write it explicitly, that it means that each element in this sequence is an element in L2. Okay? Just for your convenience. So how does the sequence look like in L2?
Sequence of sequences.
It's a sequence of sequences. So the X1, is going to be a sequence which is kind of look like maybe x1 1,
X1
x1 2, and
X3
1 3, and so on and so forth, and this guy belongs to L2. And similarly, x2 would be x21, x22, this guy belongs to L2. And similarly, xn is basically xn1, xn2, and so on and so forth, that belongs to L2. And obviously this sequence goes on to this sequence is a Cauchy sequence. So these x1, x2, xn are components. I mean, if we wish, okay, I can make a slight change. I can put a fn here, and then I say that this is f1, f2, f3. This notation is fine. What do you think? This notation is fine. If the notation is fine, I'm happy with it. Okay? So what we need to do is that first we need to find a limit for this sequence. Okay? And then we need to show that that limit is also part of L2. Both things are limit in A, but it's not in L2, it's not a still converter. So it must be in L2. What do you think, what would be the key, keeping in view these recipes actually, this description, what do you think, how we can construct a sequence whose limit is basically, are the limit of this sequence? What do you think? What is going to be the key? Keeping in view that
एक तो कुछ sequence होगी.
So one of the key insights would be that in this general term, for example, this xn, each of this is a sequence actually, and this is a sequence in what? K. And K is what? R. And we know that R is complete. And if it is complete, it means that each of this sequence is convergent. So if it is convergent, so it's like this sequence is convergent, so it has a limit actually. So this sequence is convergent, so it is a limit. Okay. So take all those limit and make a vector out of it, and we can claim that that vector would be in L2, and that would be the kind of limit of. You can ask that why each of these x1 and xn2 and xn1, xn2 is convergent, because Cauchy. Because sequence is Cauchy, so I can show that this must be also Cauchy. So if it is Cauchy, it must be convergent.
सर अगर sequence Cauchy है तो उसके सारे जो component तो भी बहुत.
That's what I would like to show actually. That's what I would like to show. So essentially, the roughest sketch is just that in this sequence. Okay, so it's like each component is itself a sequence which is converging to some limit. So take all those limits, put it in a vector, and that vector would be the limit of this given sequence. Okay, this is what I have done for. Alright, so now consider this. What would be the relationship between x and j? And for example, x and k. X and k, but x and k. Because what? Okay, let's have a look. What would be the meaning of this sequence being Cauchy? So it means that xn minus xm in 2 norm gets to 0 as n comma m gets to infinity. Okay, this is what that we are saying. As n and m gets to infinity, like this guy gets to 0. And I'm saying that this xnj is a component in xn and xmk is a component in xm. So what would be the relationship between this absolute and this basically? So we can say that this must be less than or equal to xn minus xn.
Little sum.
Okay? Alright? So if this is a Cauchy sequence, this goes to 0 as n comma m goes to infinity. So it's like it's an equivalent way to say the same thing. Okay, as n comma m goes to infinity. So what does it mean? That
X and J goes to X and K.
this implies that, this implies what? This implies that each of this x and j is a Cauchy sequence. Isn't it?
Yes.
It's a Cauchy sequence. And if it is a Cauchy sequence, what's going to happen? So it's a Cauchy sequence in K. And K is R or C, both are complete. So therefore, this Cauchy sequence must converge to something.
Now we can use triangle inequality on that.
And
We can use triangle inequality at that number.
triangle inequality, it would not be that as simple. Okay, so I'll get rid of it.
X and J is a sequence and Cauchy sequence.
Is it making sense? So each of the component is Cauchy sequence. So if it is Cauchy sequence, then what does it mean? It means that, okay, since K is complete, since K is complete, so there exists, so what should I give name to the limit? Where is this? Okay, call it Lj. Okay, Lj. In K such that x and j is converge them to Lj as n goes to infinity. Okay. So here is the next claim actually. Claim is this. Take this L, whose definition is what? So it's like L and 2 and 3 and so on and so forth. Where L1 is the limit of xn1 and L2 is limit of xn2 and so on and so forth. Okay. Okay. Claim is this. That this guy belongs to L2, first of all, and
Limit of
xn minus this L into norm goes to 0 as n goes to 2. So this is what I feel like. Okay.
मतलब ये limit है उस
Take
tag
the limit. Okay. So how can I show it? This would be a little bit not that difficult, but it should be a part. So in order to show the convergence, what we need to do, we need to fix an epsilon positive. Okay? We need to show that for this epsilon positive there exists an n such that things happen that should happen. Okay? So for this epsilon, since xn is a Cauchy sequence, okay? So I know that xn minus, okay, so what? There exists and an n depending on this epsilon such that xn minus xm in 2 norm, okay, is what? Is less than epsilon whenever n comma m goes beyond this capital. Okay. Okay? This is what. In other words, I'm using the Cauchiness. I'm just rewriting the Cauchiness of this original sequence xn. Where is it? Almost done. Consider the partial sums of the sequences in K actually. The Cauchy sequences. Going to capital M. Okay. M is some number. Consider this guy. Xn j minus xm. One thing. This is a mistake that we must have a j here. Isn't it? So it's like jth component must be subtracted. So when you subtract xn from xj, you're going to get xnj minus xnj. This must be j. Anyway, but the argument is stays. Xnj minus xnj square. So this partial sum. Okay. So I can. So obviously this partial sum is less than or equal to the infinite. It's like xnj minus xmj square. Agree? Okay. Which is equal to what? Fn. Xn minus xm from the square, and which can be estimated by epsilon square. Not estimated, but strictly. It could be less than or equal to, because when you square they might be equivalent. Okay, so it's like xn minus xm is strictly less than epsilon, but it's not guaranteed that when you square both sides, they can't be, but they can be. Or even if you wish, you can make it a strip. Doesn't matter. Doesn't matter. Doesn't matter. Now, what does this show? This shows that this partial sum has an upper bound.
Or increasing here.
And I can treat this as a sequence of partial sums, which has an upper bound, and it's increasing actually.
LCD.
So it must be convergent. So what would be the consequence of convergence actually? And let's not forget that m comma m are bigger than or equal to this n of epsilon. So what would be the consequence of this? The consequence of this would be that the consequence of this would be okay. The consequence of this would be so this is true for n and any n and any m. So if I just take one m and take it to infinity, just take one m and take it to infinity, what's going to happen? So this is going to be I equal to 1 to, for example, m xnj minus xmj, so it's going to be lj, okay, the limit, and it's a square and it can be estimated by again the square. So I'm just inserting limit n goes to infinity is. So if this is the case, what does it mean? This means that, in other words, for these partial sums, epsilon is also upper bound. Okay. And this implies, finally, okay, what does it implies finally? Shall I write it there so that everyone can see? Okay, so what you can deduce from this last inequality is that xn minus L 2 norm square is less than or equal to what? Which is equal to what? Equal to 1 to infinity, xn j minus Lj square and less than or equal to infinity square. Agree? Okay. So if this sequence of partial sum is convergent, this series is convergent, and the upper bound is epsilon square still. Okay. So monotone convergence theorem works. So if this is the case, what does it show?
xn goes to
This shows that xn minus L is what? Is less than or equal to epsilon. Okay? And for all n bigger than or equal to n, because n and m are both bigger than or equal to n, so we are not lost with this actually. Okay? And this shows that xn is convergent to L. Okay? But this is not sufficient. We need to show that L must be in L2.
सर वो अपर बाउंड एप्सिलॉन स्क्वायर लागू नहीं है इसमें इंफिनिटी वाले केस में जस्ट कन्वर्जेंट
नहीं, because okay, so this epsilon square is like upper bound for this sequence of partial sums. But since this sequence of partial sums is increasing and bounded above, so it must convergent to this supremum actually. So that supremum should be less than or equal to epsilon square. So because epsilon square is kind of an upper bound. So this is what the monotone convergence theorem is telling you. Okay? And why L must be in L2? Pretty simple. Because I can add and subtract xn, for example, okay, and maybe x capital N, doesn't matter, and L2 and apply triangle inequality, L minus capital Xn plus capital Xn, and this is finite. Okay? This is finite. Why this is finite? Because this is less than or equal to epsilon plus this xn is from L2. So the two norms of these are going to be finite. Okay. See you on next class.